All right, so there we go. Just a couple of announcements before we start. You've probably seen this poster before, but the CSAB, that is the Computing Student Advisory Board, which is a group of students that you can, it's a governing students basically, that play an advisory role to the School of Computing. If you're interested, you can join them, and you can affect change in the School of Computing or the College of Engineering. But one of the events that they're holding is tomorrow at 5 to 7 over here in Avery 19, which would be in the basement. And they're going to help you with, or Engineering Student Services is going to help you with your resume. If you haven't already put together one, then do so, because next week is the career fair, the fall career fair. Starting on, the 18th, or I guess that's also tomorrow, but that's on East Campus. So if you can make it over to East Campus, great. Otherwise, the next week on Monday, Tuesday, Wednesday, and Thursday, it looks like, they'll be on City Campus. Now, ignore the fact that, computing software and data analytics is on Monday, because every day, everybody needs computing, right? So I would recommend that you go every day. First of all, you get a bunch of swag, right? There are also other opportunities that if you're giving your cover letter, you're giving your resume out, then you're going to be getting your name into a lot more companies, and they're going to end up calling you eventually. But everybody needs computing, right? For example, where's construction? Find construction. All right, that's on Monday too. But I went one year when construction was on a different day, not for myself, just to see what it was like. And every single construction company was not hiring, construction engineers. They were hiring computer scientists, because that's what most disciplines are nowadays, is computing, right? So computing is needed by everyone, and I would recommend that you go to multiple days if you can. Even though you're a freshman, right, and you just started, you can get an internship in the next semester, or certainly next year, or this coming summer. Especially coming from the honors program, you're going to be well prepared to get that first internship in your first summer, right? So I would highly recommend that you do it. Even if you're not looking for something, or you think it's a long shot or something, that's a perfect time to go, because then it's low stress, right? You can go there not expecting anything, and stress-free. Just talk to employers, see what it's like to break that ice. All right. So hopefully you go. All right. So yesterday we were talking about functions and methods in both languages, and here I'll get rid of that too. All right, there we go. And we went through an exercise in C where we identified a prototype, right? And then we put documentation on that prototype, and then we defined a definition later on in the program. And once you've got that prototype, at least you can call or invoke that function, right? And then optionally, of course, you would want to have the return value there. Then we looked at functions in Java. Remember, those are called technically methods in Java. Very much the same thing, except that we don't have prototypes. We also have some additional new keywords here: static methods and public. Right? Static means that it belongs to the class. That just means that when you go to actually invoke it, you go with the name of the class, dot, and then the name of the function. Public means that any piece of the code can see it. So for now, we're going to make all of our methods public and static until we get to the end of the semester when we're doing instances. Okay. All right. So some other issues that you should be aware of in both languages. Some of them in one or not the other. But a method that doesn't return anything is called a void function, or a void method. Right. Method or function. That means that it doesn't return anything. You still have a return statement, but you have an empty return statement. Right. You still should have a return statement, but you don't return anything. In other words, it looks like this: return and then a semicolon, right? Now, if you have a void function and you try to return something, it will be a compiler error. If you have a return value, like you were supposed to return an integer, but you don't, then the compiler is fine with that. Remember the flag that we gave it to catch that error? The wall flag, right? Well, in Java, it's not even possible. I mean, there won't be a compiler error at all, right? But you can use the return type void to indicate that the function doesn't return anything, right? And best practice that you should still have an empty return statement right there. You can create functions with no input, and You could use void in that case. In other words, you could write, say, int foo void instead, but instead you should prefer to write int foo with nothing in it. All right. Now there are some rules there that, at least in C, that take over, but why write more when you don't have to? Right? But explicitly putting a void in there is not, doesn't make any sense. That's cruft, remember? That's stuff that should be taken out. Okay. All right, so recall that functions also only ever return one thing. Otherwise, they are not a function, right? You cannot return two things. Let me come over here and show you how we would do this in, I don't know, our demo maybe, right? So here's a void function, right? Void, do something, right? And then I take an integer n, a double y or whatever, right? It doesn't return anything. So let me go ahead and define what this function is or what it does. I don't know, maybe it prints them out. Printf n is equal to %d and the line, and y is equal to %f n and y, each on a different line. Now again, I don't need an explicit return statement here. This will work perfectly fine even with the wall flag, right? And -lm because I'm using some math here, demo.c. All right, so the -lm flag goes at the end. There we go. All right. So it's perfectly fine to do this, right? Syntactically, but it's still best practice to make sure that you've got that return statement there, that empty return statement, and it'll have the exact same behavior here. But if I change this to do something else, right, where I'm returning an integer, do something else, and I don't have anything, right? You can put void here, but that's not the way that you should do it. You should just do an empty parentheses there, right? And then do something else. I don't know. We'll printf hello, end the line, and then I'll return. Then I'll leave it like that, because remember, the wall flag will come up and say, warning, you're reaching a non-void function. Right? This was a void function. This is a non-void function because we're returning an integer, but there is no return statement. Okay? If I take out that wall flag, it will not warn me about that. Oops, too much. There we go. Right? So make sure that you're using the wall flag and fixing those errors. Return. Right? Okay. Uh-oh. Warning, return has no value, right? Because we said that we were returning an integer, but we aren't returning anything, so it's warning me about that. Here, I'll return 42 now. And now the compiler is happy with all of this. Okay. Let me try to take this over into Java and see what happens when I make those mistakes. I don't want, oops, get rid of that. And let's put this up here, and system.out. Printf. There we go. And there too, right? So that's with everything being correct, right? If I don't have an explicit return statement here, it's still going to be okay, right? But it's still best practice to put that in, right? If I don't have a return statement here, it's not even going to compile. In C, it was a warning as long as I turned on the wall flag, but here it's not even going to compile. If I try to return something that is not matching the return type, void or 4.5, it's also going to be a syntax error or a compiler error in this case. Right? So Java is a lot less forgiving because it's a lot more strict compiler. Right? Okay. All right. Any questions so far? Functions? No? Well, our code is still a mess in both languages, because it's disorganized. So what we're going to do now is we're going to modularize it. We're going to take those functions that we've been building and we're going to group them up, like these math functions over here, finance functions over there, input and output functions over there. And we're going to organize them into modules, or we call these libraries. Right? You already are familiar with a couple of libraries, the standard library, the standard input-output library, the math library. Well, now we're going to make our own libraries. All right. Why? Well, because organization, means that you can reuse those libraries. If I didn't do this, I would have every single line of code in one big giant file, right? And that's not organized at all, right? In general, libraries or headers in C should be small. You should keep those as small as possible because that's what modules are. I should be able to bring in this module, and then they should work together. If they're very, very large, right, then there's more opportunities to reach conflicts. What if I bring in a library that has an init function, which is very, very common? Init would be short for initialize, right? What if I brought in library A and library B and they both have an init function? Now we've got a conflict, okay? There's a silent rave on Friday. Great. I wonder what that means. All right, so they should be small. This also goes back to code reuse, right? You can publish your library code so that other people can use them, right? In fact, we're going to publish them so that we can use them, okay? I'm going to go walk you through a demonstration here, okay? First of all, we're going to separate our prototypes into header files. That .h file, now you know where that comes from, right? The math.h, stdio.h, they've taken all their prototypes and documentation and placed them into a header file. Then we're going to take the definitions and place them into a source file with the same name, but with an extension .c. And then we're going to compile them all together, right? And if our library is called library, then it would be library.c, but we're going to produce this new, or we're going to use this new flag here. C, actually we used that at the very beginning of the semester, if you remember. That stands for compile, but do not link. In other words, create this object file so that other people can use it. It's a binary file, right? All right, so let's do this in C. First of all, I'm going to collect everything that we've done so far, not these stupid things. I'm going to go ahead and get rid of those. But what have we done so far? We've done a factorial function, right? We've got a sign function, a custom sign function here. And over here in the AGM, we've got an AGM function. All that stuff sounds like math to me. So let's go ahead and create a new math library. Right? Come on. No, new file. Now, should I call this math.h? No, because that's the standard math libraries. What could I call it then? mymath.h? That's good enough. Have I told you before that there are only two difficult things in computer science? One of them is cache invalidation, and the second is naming things, right? And so you'll hear that all the time. Like, what should we call this? I have no idea. My math is good enough, right? And you'll see that all over the place. My underscore thing, and my underscore. Generally, what you actually do is if you're building a library, that library has a name. Then you prepend everything with that library name. One example would be GMP, which is GNU's multi-precision library. And all of their functions begin with GMP underscore. And we'll see why here in a second. All right, so I've got my header file. I'm going to grab all of my prototypes, and I'm going to place them into this one header file over here. Remember, I've got a prototype up here for factorial. There we go. And let's just go ahead and add one more here. Remember that we actually computed the sign. Let me put that into another function. But we're going to have to write that because we never actually wrote the prototype before it. All right, so computes the sign function using a Taylor series. Right, there we go. So what should I call this? First of all, it returns a double, and it also takes a double, x, right? Takes x, returns y, but sign? Yeah, remember that if I try to bring in these two libraries, we're going to have a conflict. That's called polluting the namespace. Once you create a function in C, once you create a function with a certain name, you have polluted the namespace for any other library that would want to use that name. I cannot bring in, very easily at least, two libraries that both have an init function. So let's go ahead and call this, I don't know, alternative sign or my sign or Taylor sign. Right? Something like that, something descriptive. Sign Taylor sign, I don't know. Again, difficult thing. What do we name this stuff? All right, yeah, go ahead. Oh, good. Because I'm thinking Python right now. So let me take the Python out of my head and throw it away. There we go, Taylor sign. All right. Yeah. It doesn't matter. If you want to go old school like that, just be consistent about it. We're not taking off points for it. The only reason that I would not do this in general, unless it's Python, because that's the Pythonic way of doing it, is because I'm going to kill my pinky finger always holding down the shift button to get the underscore there. Right? It's way faster to type lower camel casing here. Is that how you spell Taylor? Okay, thank you. All right, I think. All right, so let me go ahead and get rid of that. Right? Now I've got everything in my header file here. I now need to create another file, new file, with the same name. It doesn't have to be the same name, but it should. Math.c. That's going to be my source file. That's where I put my actual definitions. So let me come over here and grab my definition of AGM. Remember, we still have that to do there. All right. What do we do in the event of negative inputs? That's going to be error handling. That's what we're going to be doing next. All right. And there should have been a space there. And then what else? The factorial function right here. I'm going to copy and move that over to math.c, my math.c. And now what I need to do is I need to actually write this Taylor sign function here. And I'm going to go ahead and create repeat the prototype, or repeat the function signature, give it a body, and I'm going to take this up here, all this stuff, and I'm going to copy and paste it into here. Now here's a good question. Should we take n, that is the number of terms that we do, right? Should we take that as input, or should we take it, or we just hard code it here to 7, right? That's a design question at that point. If you want to, you can make two versions of this function. Taylor sign that only takes x and hard codes a default value of 7 here, or you can have another version that takes both x and n to specify the number of iterations that you would do here. Get rid of that because that was our example. And then finally, I need to, now that I'm in a function, once I compute a value, what do I need to do with it? Return. And what would it be? Sum in this case. Right? All right, so I've almost cleared out everything here, right? In fact, I'm going to come back to, I'm going to clear this out entirely and we'll come back to it later, right? But otherwise, there was a demo of the AGM, right? I've got all of my prototypes up here. I've got all of my definitions over here, but there's still something that I need to do, right? Now, when you include an external library, we did include and then that library. We need to do the same thing over here in my source file. It doesn't make sense to do it over here. Should I include, I'm in the math.h file, the header file. I'm the header file now. Should I include myself? No. In fact, you could, but then let me show you the problem there. Include, I'll talk about the different syntax here in a second, but my math.h, there we go. Right, that's how I'm going to include my library. I'm going to include it here and here. Let me go ahead and try to compile that now. Now remember, the flag to do that is the C flag compile. Right? So clear this out. GCC C, lowercase c that is, mymath.c. Oops. Oh, what else do we need over here in the .c file? If I'm doing math, apparently I'm doing math stuff like fabs and what else? Square root down here, pow, I guess, right there, right, et cetera, et cetera. So I need to include what? Best practice, I should include the standard library, but also in this case, include math.h. Oops. There we go. All right, now let's see if this works. There we go. All right, good. Except it didn't work. Why are there so many? Yeah, I'm still scrolling up there. In file included from my math, in file included from my math, in file included from my math. So let me tell you how it actually works. I think I talked about this at the beginning of the semester. When you include something, that's a preprocessor directive, remember? Just like define. Define pi to be 3.14159. What it does is it goes through your code, and anytime it sees pi, or what was it, kilometers per mile or something like that, right, it will actually cut and paste, and replace. What it's doing here is it's going out to this file, which you can actually go to it. I'm already in it. Right? Let me go ahead and show you over here. right? You can actually go to this file, right? It's going to this file. It's taking everything, copying and pasting it. So let me go ahead and copy everything. And then right there, that gets replaced with everything that I just copied. But what's still at the top? That. So replace it again. But I didn't get rid of it. So replace it again. Let me undo. Right. So that's what's happening. Oh, and no, I need to redo that. Right. Include math.h. Right? Or not my math.h. Right. Ever heard of recursion? We'll talk about that later. Where you're always referring to yourself. Right. So what is recursion? I don't know. What is recursion? See, what is recursion? Right. There's a joke for that. But basically what's happening is that the compiler is getting stuck in a infinite loop, always trying to replace that, but then it always comes back with another include. So it tries to replace that again, tries to replace it again, tries to replace it again, until finally the compiler just gives up and dies. Right? Error, you include like depth 200, maximum is 200. If you want to increase that depth, go ahead, but you're stuck in an infinite loop here. Right? So this does not belong in the header file. It belongs where? In the source file over here. Now this should actually work. There we go. It did not produce an a.out file. In fact, let me go ahead and remove a.out and show you again. GCC, let me refresh this. It did not produce an a.out file because it just compiled my library here. Instead, what did it do? It produced a .o file. Do you remember what that O stands for? An object file. If I tried to open that up, it'd say, that's binary. I have no idea. You can't display that. Right? If I could, of course, what was it? Hex dump mymath.o, and you can see that it's all just a bunch of binary code. Right? That is code that the machine understands that now I can write another program to link into it, just like the math library. Somewhere on this computer, there is a math.o file for you. Right? It's actually probably more complicated than that. It's probably an SO file, which is a shared object file. In Windows, we call these DLLs. Right? Have you ever heard DLL before in Windows? Right? It's a dynamic link library. And then you get into DLL hell. Right? Because where did I put that thing, right? And the compiler can't find it. Windows can't find it, or it gets corrupted, and now none of your programs work. Right? I had to deal with this a while ago with some game that my kids downloaded from Steam, and then a DLL got it corrupted, and we had to manually delete it. Or what do you do at that point? Uninstall, reinstall, right? Something like that. But anyway. We don't have to deal with that because it is right here in the same directory. Right? Now let me go over to my demo over here. Right? And actually, yeah, let me grab this over here. And let's go over here to the demo. All right. And I'm going to read in two numbers from the command line. I guess I hard-coded them here. So let's just go ahead and hard-code them as well. 6 and 4. And remember that I grabbed this expected result, 13 point something. That was from Wikipedia. And then I called that AGM, and then I print out the result. Here's the AGM of these two numbers, and I actually expected this. Are they the same thing or not? Right? If I tried to compile this as is right now, GCC demo.c, right? Lots of problems. Let's go ahead and scroll up here and find out what the problem is. First of all, does it know what AGM is? Nope. So the first thing I need to do is I need to bring it in, just like I brought in all these other libraries. Include mymath.h. Now at this point, I'm going to point out the different syntax here. The Langle-Wrangle, that is left angle bracket, right angle bracket, we call it as Langle-Wrangle. That is if it's a standard library, something that gets shipped with the C libraries, right? And so what that's going to do is that's going to tell the compiler, hey, don't bother look in the regular places for this. Where they are, I have no idea. We'd have to go down a rabbit hole to find them on the system. But they're somewhere on the system, and it's been configured that the compiler can actually find them. Right? I don't know. Maybe that's worth it. Use GCC to find the location of a library. Can we do that? How to specify? Nope. I want to know where they are. Where should library be located for development? Blah, blah, blah. What's the answer? Probably user local include, or, okay. ls user local include. Nope, not there. ls user local. What are the other alternatives? This is target include. User target include. Nope, not there. I'm not going to go down the rabbit hole any further, right? I don't care, right? In any case, I need to include this. So again, the Langle Wrangle, that is for standard libraries. If you put a double quote here, what it says is, compiler, this is not a standard library. This is a library that I have created. Go ahead and look for it in the current working directory. If you can't find it there, then start looking in the system folders, right? And since it's already in the current working directory, .o, then it's going to look there first, okay? Now it still will not compile. Let me go ahead and try. Different result here. Instead of a warning saying I have no idea what AGM is, now it does know what AGM is because I've included this header file. It's got the prototype, but it doesn't have the definition. Now, if this were a math library thing, I would use -lm, right? And I'm going to have to use that. But to link into my library, what I do is I include the object file at the command line, my math.o. There we go. So I don't need the hyphen at link. The hyphen L means link, and then M in this case stands for the math library. In this case, though, it's just simply take that object file and that source file and compile them together. That produces an a.out file now. And let me refresh over here to show you that it is indeed there now. All right, was that correct? Yep, looks like it to me. It's close enough at least. Okay. So again, you separate prototypes into header files. You separate definitions into .ce files. You compile them together with that .ce flag, and then you can compile. You can include them in a source file using, remember, include and then library.h, whatever it is. That, again, that double quote there is for non-standard libraries, user-defined libraries. Then compile all together to create an executable file using GCC and then the library name, library.o, and then the main.c, and then -lm if you need it, or a -wall, or whatever else you want. Okay? So all those things together. Again, you don't need to be doing this for your lab and hacks this week. You don't need to be doing this for your exam next week. In fact, you're not going to be able to do it because you're not going to be able to hand in multiple files to code post. But you will go through this process in week 6 after we come back from that first exam, and you'll be doing this. All right? And I'll remind you how to do this that week as well. All right. So that's pretty good. What about in Java? Java does not have prototypes. Instead, collections of methods are separated into utility classes. Right? Classes are organized into packages, which we've already done. Right? For example, UNL SOC. Remember that creates a UNL folder. Within that, there's a subfolder called SOC. And then you can put related classes within that folder. And then within each class, you can put related methods. So if I were to do the same thing over here in Java, I would want to create a brand new class. I'll call it myMath, right? Just like we called it myMath over in C. And then another, you might also be wondering, why did I switch over to underscores here? When you're talking about files in C, generally you do underscores. But when you're doing classes over here in Java, you use upper camel casing. Okay. What have we over here? So let me go ahead and grab, I'm just going to go ahead and grab all this stuff. All right. Now the main difference here is that everything will be prepended with public, static, right? Public, static, And I do not have prototypes. Instead, I need to provide the definition there. The definition. All right, there we go. And I can reformat everything. Now, it's not compiling because I do not have return statements. I don't have the actual code yet, but I can go ahead and copy paste that stuff too. Right? So here's my AGM implementation. And I'm doing this straight from C here to remind you that is there really all that much that's different? Not that much. What's different though? Math.abs. What's different about square root? Math. Because in Java, everything is a class or belongs to a class. It's organized into classes. All these math functions are over in the math class. Right? There's one. And documentation. There's another. What is that? CBRT? What is CBRT? The cube root of a value. There we go. Right? For whatever reason they called it that. Right? Factorial, there is definitely not a factorial implementation, but we've got our implementation over here. Here, I don't think that there's going to be any change at all whatsoever. Right? Over here, with the Taylor sign, right? I don't think that there's going to be any change there at all either. There. Okay. Right? Yeah. No. Oh, there is something. What's wrong? Pow. There we go. Thank you. There we go. All right. Note here, factorial. Where is that declared? Up above. Does it have to be? Right? What if I were to relocate this to the bottom in Java? Does order matter in Java as far as the order of that you put the methods in? Doesn't seem like it to me. Does it matter over here in C? Likewise, no, because what have we already done? Remember over here in demo, we included the entire H file. We didn't include the definitions, right? What we did is we included all these prototypes. Right? So that was technically included before we used it down here, where we call AGM. It is enough to bring those in as header files. If I didn't do that, right, then it would not know what you're talking about, and it would be at least a warning here, right? Yep, at least a warning, implicit declaration. It'll probably still run, but that's because we're getting away with it. Oh, no, we're not getting away with it. Thank you. Well, yeah, what's wrong? Yep, it has no idea what it is. So what's happening here is those arcane rules of if you don't have a return statement, what happens? It starts returning weird stuff, and that's the weird stuff it returns in this case. Okay, so restore that. And it is important, but the order is not important. Okay? Including it is important. All right. Any questions so far? We're a little bit ahead this semester because, was it last week or is it this week that we were planning? Last year there was a football game on a Friday during the day. There's still a football game on Friday, but it's in the evening, right? It's not this week, it's next week. All right, no football fans. All right, never mind. Anyway, or maybe it was a volleyball. No, there's been volleyball before, but they've held like day games and they've told everybody to cancel classes. That's not happening this year. So we're a little bit ahead. We're a little bit ahead. All right, so what we're going to do now is called unit testing. All right? A unit is a piece of code, usually a function that can be tested. In fact, that's the default kind of unit in code, okay? But ultimately, a unit is an indivisible piece of code that should be treated as a black box. Right? A black box means that you want to test things in isolation. The stuff goes into the black box, stuff comes out of the black box, but it's black, so it's opaque. You can't see inside of it. You're not supposed to be able to rip it open and say, oh, okay, well, what happened here? When you debug, you open it up, but unit testing itself tests it in isolation. A unit test, as you've already seen, is a pair. It's an input-output pair that is known to be correct. For example, I know that if I input 6 and 14 here as my inputs, then my expected output should be 13.458 and change there. Right? That's a test case right there. Right? Now, I'm going to get the result, And I'm going to output then I'm going to test the result, the actual result versus the expected result. Are they the same? Okay. And that's what a unit test is. We test by feeding the input into the unit or the function and comparing the result to the known correct output. That is the actual versus the expected. If they match, and I'll put that into quotation marks there, match, then it passes. Right? If they do not match, then it fails. Right? And of course, you want all of your unit tests to pass. Okay? All right, so let's come back to this after we've looked at a way of doing this over here in C. This is going to be informal unit testing here. I've already got my units. I've got my unit test right here. I've got my input and my output. And then I'm going to grab the actual output, actual result, we'll call that. Right? Now, I could just print it out and say, okay, yeah, that looks good enough. Right? But I want this to be automated. I don't want to sit there and have to run it okay, yeah, that number looks correct, that number looks correct, that number looks correct, right? That's how we usually have to grade, by the way. That's why when you output like your table this week of figures, the grader is actually only looking for specific lines and says, yeah, that line is there, and it's down correctly to the correct cent, right? That's why if we had to, string match the entire thing, that means that all your little white space would have to match too, right? And we're not going to do that to you, all right? Later on, we have to do it up front because we haven't done unit testing, but later on, we'll give you full unit tests. You can run them locally, and it'll run 1,000 tests, and it'll say 998 of them pass. Here are 2 that fail. Focus on those, right? Then you'll write your own unit tests. But we want it to be automated, right? I don't want to output this. Right? I want to write code to check it. Right? If the actual result is equal to the expected result, this is my first attempt, by the way. It's not correct. We'll find out why here in a second. If they're equal, then it passes. Right? Else it fails. Right? Okay. So what does passing mean? Well, I can output printf test case 1 pass. Right? And then end the line. Test case 2. Or test case 1 fail, right? We like that pass fail because it's both 4 letters, and so they're all going to line up really nice, right? But if it fails, what I also want to do is I want to output some more information, right? I'll say that %f is not equal to %f. And I'll output the expected, ooh, come on. Okay, there we go. Expected result and actual result. There we go. All right, and then also if I'm going to have multiple test cases, I can copy paste this boilerplate code here, and I can reset X and Y. Give me another X, and give me your favorite numbers. 42, oh, that's my favorite number. Right. Say what? 7, all right, lucky 7. Right. Now what is our expected result in this case? Should I run the program, see what it outputs, and then put that back in there for the expected result? No. I need to pull out, that would be not designing a good test case, because it would assume that my code is correct. You need to use something else. In this case, you can use Wolfram Alpha. Right? What is the AGM of, we said 42 and 7? There we go. So that number right there, I'm not going to copy it all, I'm just going to copy a chunk of it. There we go. And there's my expected result. Here's the actual result. And then I have the exact same code over here, but now it's test case 2. 2 and 2. Right? Well, if I'm going to have multiple test cases, I probably also want a summary. Right? So what I'm going to do is I'm going to create more variables here, int num pass and int num fail. That's why we like pass fail, because again, everything's going to line up here. Right? And if a test case passes, we can say num pass plus plus. We can say, if it fails, num fail plus plus. And that way, we can actually have a summary at the end here. Num fail, pass. There we go, pass. And we'll printf past percent d and the line, num passed, and failed. Again, that's what it all lines up nicely. Num failed. Right? And then you can even put out a summary here. Percent point 2f, right? There we go. And what would be the percentage? Num passed divided by the total, which would be num passed plus num failed. Careful, those are all integers. What should I do? This is all either going to be 0 or 1, right? Yeah, typecast double. All right, I like that. And since this is called, usually I would rename this as like a test instead of demo, but we'll leave it for now. Right? All right, num fail, duh. There we go. Did I make that mistake anywhere else? Thank you. There. All right, let's run this and see if it works. Now, if my code is correct, I should see 100% there. And I should see 2 out of 2 test cases passed. Both of them failed. 13.48, whatever. Wait, that's exactly the same over there, right? And that's exactly the same over there. So what's going on here? Equals equals. Tell me what that does. Yeah, go ahead.
Does it look if they're in the same place in memory?
Not in this case that they're the same place in memory, but that they're the same all the way out, right? And remember that I have a tolerance in there in my AGM, right? If it's to within 0.00001, right, then it gives you that answer. I need to build in a tolerance here. Instead of looking at strict equality, I need to know, are they close enough, right? So let's take that tolerance, double tolerance, and say 0.0001 or whatever it was, right? And as long as these two numbers are close enough, in other words, the absolute value, fab's absolute value between the difference is less than the tolerance, then it passes, right? Because it's close enough. You're never going to get something that's exact because computers are not exact. They are finite machines. This is probably this might be an irrational number that goes out forever, right? But if I build in a tolerance, then yeah, it'll work. Right? Oh, and it should be 100, right? Times 100. There. Okay. That'll look nice now. Oh, and then I also want a percent sign there. But guess what? Percent. That's the placeholder. Right? So I can do 2 of them. Or an alternative would be to escape it. I think that this will work and see. Let's find out. Okay, no. It doesn't like that. It wants 2 percent signs. There. Oh, looks nice. Real nice. Now you can go ahead and align everything if you want to. Right? Let's add another test case here. I'm going to test a whole bunch of stuff. I want to test factorial. So int input to the factorial will be, I don't know, 5. Int expected result is equal to, what's 5 factorial? You can do this in your head, right? 5 times 4 times 3 times 2. 120. Good. All right, and int actual result is equal to a call to that factorial function of the input. And then I can check if. Now here, do I have to use that fabs trick here? I want to know if the expected result is equal to the actual result. Equal to the actual result. Equals equals will work in this case. Why? Because they're integers. If they're off by more than 1, then that's not acceptable, right? 121, 120, they're not close enough, right? So I will go ahead and use the equals in this case. Integers, use equals. Floating point numbers, build in a tolerance because you'll never get it, right? Expected result, so you can cut and paste this stuff. All right. There we go. But this is test case 3, test case 3. And by all rights, I should be doing this in a different file because unit testing, we would want to test the factorial unit. Then we would want to test the AGM unit. Then we would want to test something else. We want those separate. But this is just a demo, so it's good enough, right? And this is not %D. And the reason that you would want to separate these out is because it won't compile at this point because I've got multiple definitions of expected result and actual result. Remember that I did them up here as doubles, right? Down here I'm doing them as integers. This is why I would want to separate them out, right? So if you want to, you can go ahead and put factorial input, right? Or something like that. And now I'm in Python land, sorry. There we go. Expected result, factorial, actual result. Same thing here. Actual, expected, the actual. I think I fixed everything. No. I typed it, but there we go. It's not my keyboard, I'm pretty sure. This would be factorial input. There we go. All right, 3 test cases passed. But copy paste, and then I had to change all that stuff to factorial. It's a lot of what's called boilerplate code, right? This if-else statement, and then I increment plus, minus, or plus on one or the other, right? Why should I have to write that? Right? And that's what we'll be doing after the break. I'm not going to write that. I'm going to bring in a library to do it for me, right? I will, however, specify the input, the expected output, and then that library will take care of everything else for me, right? All right, any questions? Otherwise, we'll continue it there on Friday. No? All right, I'll see you on Friday. Again, remember, you've got those opportunities ahead of the career fair next week.